Conjunctivitis, commonly known as pink eye, is an inflammation or infection of the transparent membrane or conjunctiva that lines your eyelid and covers the white part of your eyeball. When small blood vessels in the conjunctiva become inflamed, they are more visible, and that is what causes the whites of your eyes to appear reddish or pink. Conjunctivitis can be caused by viruses, bacteria, allergies, or irritants such as foreign particles that enter the eye. Viral and bacterial conjunctivitis are highly contagious and spread through direct or indirect contact with the eye secretions of an infected person. Common symptoms include redness, itchiness, a feeling of irritation, and discharge or tearing from one or both eyes. Treatment typically focuses on relieving symptoms. This may involve using artificial tears, cleaning the eyelids with a wet cloth, and applying cold or warm compresses. For allergic conjunctivitis, antihistamine eye drops may be prescribed. If it is bacterial, antibiotic eye drops or ointments may be necessary. Good hygiene practices are crucial to prevent the spread of conjunctivitis, and while the symptoms may be quite uncomfortable, they rarely affect vision. Welcome back to another episode of Polymer E-Club's Ask Dr. Paul. Today we're going to highlight how modulus and temperature limits are created by thermoplastic elastomer hard and soft segment composition. So when your boss talks about property boxes of molded TPE parts and products, what do you need to know? In a previous That's Working Knowledge video, we discussed the Thermoplastic Elastomer Modulus and Temperature Properties box that can be created with each TPE material and grade, since plastics and elastomers are so distinct related to properties. Their modulus and temperature upper use limits will be bound by the hard segments of the TPE, and more specifically the TG of an amorphous TPE or the TM of a crystalline TPE, while the flexibility and low temperature limit in which the TPE will remain flexible is bound by the soft segments, and more specifically the TG of the soft segments of the TPE. As we increase temperature moving left to right, the TPE transitions from a rigid state, which is unusable as a TPE, to a flexible state, which is usable, to a melting state, which is unusable as a TPE. Therefore, with low and high temperature extremes, we exceed the ability of the TPE to function. On your screen is your reminder that besides modulus and temperature, tensile, tear, and abrasion are hard segment dependent, and the hard segment levels drive the property values, while the soft segment levels drive TG, hardness, low temperature flexibility, elongation, compression set resistance, and resilience. You can see on your screen a table of thermoplastic olefin properties, specifically in gauge grades offered from Dow DuPont. And if we increase the hard segments by going right on the table, we increase crystallinity, density, and hardness. And with tensile and flexural testing, we increase modulus strength and decrease elongation. From DSC testing, we increase TM and TG, and we can make some interesting plots with this data. We can make a box up and to the right, that is the dark blue box, by increasing the hard segment levels of the TPO, because increasing hard segments will increase crystallization, modulus, and TM. Talking numbers, as we increase hardness, the modulus increases from about 4 to 72 megapascals, and the melting temperature increases from 38 to 96 C, driven by the hard segment high-density polyethylene. And we can make a box down and to the left, that is the smallest light blue box, by increasing soft segment levels of the TPO, because additional soft segments will increase flexibility and will decrease modulus and TG. And thus we see 3 modulus and temperature blue boxes from 3 TPO grades. If we want to move the box significantly left or right, we will need to choose a different TPE type. For example, we know that polyethylene-based TPEs, like Engaged TPO, have melting temperatures mostly below 100 C, while the PBT-based TPEs, called TPC, have melting temperatures around 200 C, which would significantly move the temperature box to the right. Here are some thermoplastic copolyester properties, specifically Hytrel grades offered from Celanese, and we see much higher modulus and temperature values than the engaged TPO grades. And again, if we increase the hard segments, by going down on the table, we increase crystallinity, density, hardness. With tensile and flexural testing, we increase modulus strength and decrease elongation. And from DSC testing, we increase TM and TG, and we can make some more interesting data plots. We can now add a high hardness TPC to the 3 TPO plots, that is the red box, which is significantly up and to the right with a high modulus and melting temperature compared to the TPO data. Then we can add lower hardness TPC grades, and you see how these two red boxes are middle and down and to the left by increasing soft segment levels of the TPC, because the increased soft segments will increase flexibility and will decrease modulus and TG. Talking numbers, as we increase hardness with the 3 TPC grades, the modulus increases from 21 to 190 megapascals, and the melting temperature increases from 177 to 200 C, driven by the hard segment PBT, while we increase TG and diminish flexibility, all driven by fewer soft segment ether copolyesters. Knowing that different thermoplastic elastomer grades and types will have different modulus and temperature property boxes, that's working knowledge. Remember to like, subscribe, turn on notification, and even share if you appreciate the content. You can visit our website to learn more about our upcoming Flexible Polymers course. I'm Paul Nash for Polymer E Club's Ask Dr. Paul. Thanks for watching.